Back to the afternoon session, and it's my pleasure to introduce Professor Torstein Nilssen. He finished his PhD from University of Oslo in 2013. He did several postdocs at many places like Humboldt University in Berlin, University of Manchester, and eventually he came back to Norway and joined University of Agder in 2019 as an associate professor. And he's going to talk about Euler equation part out by rough noise. So yeah, floor is all yours now.
Thank you. And now can everybody hear me? Yes? Great, perfect. So first of all, of course, thanks to Ujjwal. Thank you so much for inviting me. I've had a really good time here, and fortunately there's another week, so we'll still have more good times. So what I'll be talking about is Yudovich theory. For rough perturbations of Euler. Okay, so let's see, what are the goals of these 5 lectures? First of all, I'll give an introduction. So, just an introduction to the type of problem that I've been interested in. So, these are noisy equations. Someone could think that, okay, regularization by noise is an interesting phenomenon, but it's not necessarily what I'm after. So I'll also talk a bit about my motivation, and we'll look at sort of what's the correct, physically correct equation that we're going to study. So physically relevant equation. Second of all, I'm going to give a quite comprehensive introduction to rough path theory. Is it big enough? Everybody sees what I'm writing? Yeah? A little bit bigger, okay. Comprehensive intro to rough path theory. Is this better? You see the last part? Perfect. And then finally, we will take the things that I've proven in or what's included in the introduction to rough path theory, and we will apply this to so-called Yudovich theory for Euler's equation. So apply to obtain or to get, let's say, obtain Yudovich theory. Okay, and by Yudovich theory, I mean here that we're going to prove well-postness of this Euler type equation. So we're going to prove here well-postness in vorticity, or let's say for vorticity in L1 intersected L infinity. And by the way, Yudovich theory is all R2. So, really the major part of what I'm going to do is to do this introduction to rough path theory. This application to the Yudovich theory, the Yudovich theory is from the 60s or something like this, so it's quite old. It's nothing, at least compared to the other techniques that we've seen here so far, it's nothing fancy, okay? But my main goal is to have you understanding rough path theory. All right, so let's just start. And I think by now, we're quite familiar with Euler's equation, but let me write it once more. Okay, so here we have Euler's equation, and we recall that the solution is actually a pair of functions, u, which is a vector field, and the pressure, P, which is a scalar. Right, like this. Okay, so now let's just pretend that we're looking at some fluid and we're trying to replace some infinitesimally small fluid particle into the fluid. And then we wait, we see what happens. So we try to trace the behavior of the fluid particle around. And in mathematical terms, what you would do is that you would sort of take the solution of Euler's, of course this is divergence free. What you would do is that you would take the solution of Euler's equation and you would solve an ordinary differential equation, right? And this is what you obtain is what you would call the Lagrangian trajectories. Lagrangian trajectories. And you obtain them by solving this ordinary differential equation. Okay? And so, by the way, when I'm writing subscripts for the time parameter, I mean, it's not like it's the derivative with respect to t here. That's the dot. And also for u, time dependence is a subscript. Okay. Well, it turns out that Lagrangian trajectories you can actually observe. And so I will just, maybe I should have shown the picture, but okay, no, let's not do it now. So there is a very nice paper by Prisan, Franco Flandolet, and Darrell Holm from, let's say, 2020, I guess. Do you remember? Yeah. 2020, I think, where they show a very nice picture of Lagrangian trajectories. And more specifically, what they do is they have a map, and it shows the Pacific Ocean. Right, so this is the Pacific Ocean here. And in the picture, it's full of many little squiggly lines. So you have little squiggly lines going like this. And let's take a different colored one, squiggly line going like this. And another one. And I mean, they really take up the entire picture. So squiggly line going like this. And what it represents is actually so-called drifters. So people have been placing drifters into the Pacific Ocean, something like 10,000 since the 1970s. So it's just, well, it's a drifter, it's placed into the ocean, it's floating around in the ocean, and it's sending signals to a satellite about its position. So meaning that you can really trace it, you can really trace how it's moving around. And of course, these little drifters are quite small, I mean, at least compared to the huge ocean. So it's natural to think of this as Lagrangian trajectories, like infinitesimally small particles floating around. And yes? 18, okay. 19, okay, almost. Let's see. Good. Oh, actually, I have the paper here, I could have just... But what they observe is that the Lagrangian trajectories are quite irregular. And so this is, I'm just reading now from the paper. It says, each color corresponds to a different drifter. And you should really see the picture because it's much better than what I'm able to draw here. So each color corresponds to a different drifter. And they write, upon looking carefully at the individual Lagrangian paths in this figure, one sees that each of them evolves as a mean drift flow composed with an erratic flow comprising rapid fluctuations around the beam. So that there really is this type of erratic behavior to the Lagrangian trajectories. Okay, so now, based on this observation, they suggest a model. So we suggest a model. And the model is on the form that phi dot we should decompose the Lagrangian into mean drifts plus this erratic flow. Okay. And also, like Mario explained to us, that sometimes things that are fluctuating very, very quickly, that's very erratic, it can be difficult to model. It can be nearly impossible to understand really the dynamics that goes into this type of behavior. And so if you have a term which is very difficult to model, it could be a better idea to just replace it with something random. Just say that, okay, it's so difficult to understand this term that we just replace it by a random term. So we put this mean drift, and here we simply put something random. Because in any case, if you're trying to model this, and there will be lots of uncertainty in your model. And introducing random terms in the model can give you a way of sort of parametrizing the uncertainty that you have in your model. Okay, and then we choose to write this mean drift. Let's write this as qt of phi t, which would somehow, in some sense, be the solution of some modified Euler equation. And this random term, we add it like this. Psi k of phi t times z dot k. Okay, and of course here I'm using k here means the summation of repeated indices. Okay, and here, so z should represent some type of noise influencing the dynamics. So z, z1 up to z capital K should be irregular and represents the noise of the dynamics. Represents the noise or uncertainty in the model. Okay, so I mean, this is just some k-dimensional path. Oh, I should have written. So this is going from 0 to t, taking values in rk, right? Okay. What about the vector fields? So psi k, going from 1 to capital K. For these lectures, we're just going to assume that these are given vector fields. They're just sort of somehow given to us. Fixed vector fields. And in practice, what one can do is to choose, let's say that now you have some observable data. What you could do is that you could use these vector fields to fit the model to data. So can be used to fit model to data. Model to data. And we actually have some, let's say, baby steps in this direction. So there's, let me just write, okay, this is Leahy. So it's James Michael Leahy and myself, and from 2024, I mean, okay, it's on the archive, it's under revision, so it should be out soon, hopefully. Okay, but we're not going to talk about that. We're just going to assume that these vector fields are given to us somehow. Sorry? zk? No, psi? Yeah. These are vector fields, yes. Yeah, for each fixed k, this is a vector field. Mm-hmm. Yes, divergence free. Yes. Mm-hmm. More questions? Okay, now I could say that in the very beginning, I started with a PDE, and then I said, oh, well, let's look at the Lagrangian trajectories. Like, take the solution, solve this ordinary differential equation. But here it's a bit like I'm going the opposite direction. I'm sort of saying, I want this to be my ordinary differential equation. And then a natural question that pops up is like, what's then the corresponding PDE? So we have a theorem. This is by Dan Crisan and Darrell Holm, James Michael Leahy again, and myself. And this was 2022, I think. And okay, and this is based on works by Darrell Holm. On Holm from 2018, I guess. Where we show that so physically correct, physically relevant equation is on the form dt of u plus u grad u. Let me leave a bit of space here. And then the noise should appear in this sense that you have the vector fields are transporting the solution, but you should also put a multiplicative term here, where you take the derivative of psi k and then you multiply it with the solution. This is equal to 0. And of course, it should still be divergence free. Okay. So, Laszlo, you didn't like it? What do you mean? Should it be a minus? Yes, I really do want it to be, okay. Yeah, okay. So, no, but are you sure it doesn't matter? You have a pressure. But I mean, it's not, okay. It should be plus? My feeling was also plus. Okay. Yeah. I mean, okay, maybe it's not a good idea to have feelings about mathematics in that sense, but I do believe it's plus. Okay. So in this noise term, we see, okay, first of all, something that looks kind of like the nonlinear term. So this is maybe not so surprising. It looks kind of like this. But what maybe looks a bit different is that you have this multiplicative term. But in some sense, you can imagine that this is already in Euler's equation. I mean, you could write the equation on this form here. And then what you would do, you can notice that du times u can be written as the gradient of 1/2 u squared, so that this term is just a part of the pressure. And here I agree, plus or minus doesn't matter, right? Yeah. Okay, so why do I say physically relevant? Well, at least formally, it conserves entropy and something called the Kelvin circulation theorem. Is still satisfied by this type of equation. So, I mean, of course, it depends if this is something you want your model to preserve, if you wanted to still have this Kelvin Noether circulation and entropy. Entropy conserved. I mean, of course, these are difficult questions to ask if you really have a solution because it depends so much on the regularity and so forth. But it's just for assuming everything is smooth. Yes, Laszlo? No, this? No, but can you really write it as a... Yeah? Is it? No, but don't you get an extra term from psi? Okay. Yeah, okay. You don't want the gradient. I don't want the gradient. Mm-hmm. No, it's fine. Yeah, we can do the computation later. And in fact, okay, maybe I should have said this before this interlude that, okay, it's not going to be so important for us because in any case, we're going to pass to the vorticity formulation in 2D where we actually don't see this term at all. Okay, so you might say now that, well, that's a really nice equation, or maybe Laszlo doesn't think so, but the rest of us think it's a very nice equation. And the next question is, of course, now can you solve it? Can you really do something with it? Now the question is, can we solve the equation? Okay. So let me now just sketch briefly how we're going to attack this question. And we're going to work only when the dimension is equal to 2. So we take d equal to 2 and define the vorticity. So I mean, I guess this was already done in Mario's talk and also other talks, but we now define the vorticity as the curl of the velocity. And again, you have to help me to see if there's a correct sign. Should it be partial 2 u1 minus partial 1 u2, I guess? Yeah, exactly, yeah. Can we show well-postness of this equation? Or, yeah, do we understand anything of this equation? Yeah. Okay, and so we can define the vorticity, and if we take the curl of this equation, we get that the vorticity should satisfy this quite nice equation here. Right. So we get a very nice, nice equation that looks like a transport equation, which is somewhat much nicer. Of course, it's still nonlinear because u, right? U is omega depends on u, and we can actually recover u by the Biot-Savart law. Which means we can say u is equal to k convolution with omega, and here k z is z perpendicular over 2 pi and then absolute value of z squared. Yes?
I saw also Mario's lecture.
Uh-huh.
You always choose a noise of some form, so that at the end you get some equation like this.
Yes, yeah.
You have well-defined Lagrange.
Yes, and that's exactly the point.
That's the motivation, and that looks to me like artificial, and I'm not
Yeah.
I don't know much
So,
about the...
okay, so there was this, there are these arguments from geometric hydrodynamics that we used in order to say that this is sort of our correct, yeah, that it should really take this form, yeah.
At that end, I see it's very nice.
Exactly. And in 2 dimensions, it's very nice, right? Yeah. But these are really like Lie derivatives. I mean, if you formulate everything correct, then I guess U should not be a vector field, but the one form induced by the vector field, by the velocity, and then sort of you can rewrite this as a Lie derivative of U acting on U, or be U flat. So yeah. But you think it's especially nice in this setting. Yeah. Good. So we get a very nice transport equation, and as I'm sure you already know, what's so nice about transport equations is that we can use the method of characteristics. So we can just we can actually compute the solution if we have the flow generated by the vector fields. But so let's just show this. So in case somebody doesn't know, of characteristics. So what you do, you imagine that you have the solution of this equation, and then you plug in the flow, meaning the solution generated by these vector fields here. And then you look at how this changes in time. Okay, so for now, assume everything is smooth. Like it's not like in Mario's lecture where you had this E2 correction term or anything like this. Pretend everything is smooth. So we just have usual calculus rules. Right, and then d omega t of phi t, and then phi t dot. And now we plug in phi t dot, what it should be. And we can see what we obtain is dt omega t plus ut gradient omega t, and then plus psi dot gradient this and zt. And everything is evaluated in the flow. But here we recognize, of course, this is the solution we started with. So if we have a solution, this is certainly equal to 0. Good. So it means that the vorticity doesn't change along the characteristics. So phi omega t at phi t should be constant. In particular, it's equal to the initial condition. Right? And then we can hope to write omega t as omega 0, so the initial condition evaluated in the inverse flow. Right? Okay, so now we're in good shape, because now we have seen that. Okay, so the vorticity can be just written in terms of the inverse flow. So it just depends on the the ordinary differential equation. Right, and we see that, well, the ordinary differential equation is generated by the noise. This is fine. This is sort of given to us. And the drift vector field, U. But U can be again recovered from omega. Okay, so we see, and omega can be recovered from the flow. Okay, so you see we get into this circular argument. So now we can somehow hope to set up a closed set of equations that describe this. Okay? And this is really the heart of the Yudovich theory. So what we will do is we will look at a purely Lagrangian formulation. i.e., so we will look at the flow, which should have this decomposition. We want ut to be recovered from the vorticity, so it should be a convolution with this kernel that I wrote over here. And omega should be given just by the inverse flow. So, and again, this was discovered, I mean, this was done already in the 60s or something, without the noise, of course. Yeah, okay, so I mean, now that's the question. What is ZT? So because I said that it should not be differentiable. Yeah? So Z not differentiable. And your typical example would be a sample path of the Brownian motion. Yeah, so in that sense, yes. Sample path of Brownian motion. And there were some people who had never seen the Brownian motion before. Yeah, okay. Let's just write it up real quick. So I mean, I know Mario did this, but it's good to have a recollection of this, especially if you're seeing it for the first time. So B is a stochastic process on some probability space. And I guess you've seen probability spaces, right? Yeah, measure theory, great, perfect. A stochastic process on some probability space such that Bt minus Bs, the increments of the path should be Gaussian. And the covariance matrix is given by T minus S times the identity matrix. Okay? This is one condition, and it should also be independent. Independent of, say, Bs1, Bs2, dot, 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 up to Bsn, where S1 less than S2 up to Sn less than S, oops. Sn less than S, less than T, like this. Okay, so the increments are independent of where it came from. Good. And then you can say, well, if I wanted to consider that Z was like a sample path of the Brownian motion, if I'm very interested in the Brownian motion, you would say, well, okay, you can use Ito theory. So then we could use Ito theory. Ito theory to understand this term, this noisy term here. Okay, one problem with the Ito theory is that it's really hinging on this independence of where it came from. Increments should be independent of the path. And it's really best suited. So best suited for memoryless noise. Okay, and it turns out that the oceans have memory. Okay, so I'm not trying to sort of personify the ocean in any way, but there are some papers that shows that the fine scale dynamics of oceans is sort of positively correlated, no, not positively, correlated to where it comes from, correlated with its past. No, no. Okay, so in the picture, the reason that they were intersecting was because they were simply just different paths, different drifters that are just floating around. Yeah. And I mean, they're placed into the ocean at different times and so forth. Yeah. You would expect them to really cross. Okay, so, and the Brownian motion doesn't have this. It cannot really, the increments are really independent of its past. Now there's another very famous example of a stochastic process called the fractional Brownian motion, which is much better suited for incorporating correlation with its past. So let's say a definition of FBM, or fractional Brownian motion. So it's a Gaussian process. Gaussian process, let's call it BH with covariance so this is equal to, let's see, what is it? 1/2 t to the 2h plus s to the 2h minus t minus s to the 2h, like this. Yeah. And this is what's called a fractional Brownian motion. It's called fractional Brownian motion. It should be between 0 and 1. Yes, I'll write it down. No, but that's good. Yes, we should definitely say this. H between 0 and 1. And this is a stochastic process which has memory. And it turns out that when h is larger than 1/2, the increments of the process are positively correlated with its past. So increments, say BTH minus BS is positively correlated with past. When h is less than 1/2, it's negatively correlated with its past. And when h is equal to 1/2, in fact, you get a regular Brownian motion. Okay, so and E2 theory really cannot deal with this. Okay, there is something, for those of you who might have heard of it, something called white noise calculus, which is a vast generalization of the E2 theory, where you, in principle, can look at fractional Brownian motion, but it's really difficult. It's not really clear that you can implement such a thing. And even worse, if you consider the calculus using this white noise approach, it would completely break the structure of this geometric structure of the equation. Like, for example, you would no longer get the transport equation like this, and no longer have this nice form of this Kelvin circulation or entropy balance or anything like this. Okay, fine. But now, okay, so E2 theory is not well suited for this, but now comes the rough path theory, and this is where we'll now start our journey into the rough path theory. So, yeah, so that's it for the introduction. Now let's go to the rough path theory, so the second part of the goal. Sorry? Why it exists? I don't know, some type of Kolmogorov consistency theorem. I guess you can use it to construct it on some very large omega space. I don't know if there's something similar to like well, I mean, if the Kolmogorov extension theorem is a way of constructing the Brownian motion, but somehow, so I don't know if there's something like the Wiener measure on path space. I don't know. And also, well, what I just mentioned, this white noise calculus gives you a way of constructing fractional Brownian motion. It really exists. Good. Okay, so this is where we're at. So now we want to try to understand this term, and we don't want to use E2 theory. It's simply not suitable for the source of noise that we want to consider. So instead, we will look at the rough path theory. Okay, so we will leave Euler's equation aside now for, I mean, maybe we won't get back to it until Friday, but let's see. So in order to just simplify as much as possible, let's just imagine that this term is not here, right? This is a very nasty and should satisfy some nonlinear type relation here. So let's just remove it. And let's see, can we understand this type of equation? Let's start there and then we build on this afterward. So first, let's just say that this drift term is just equal to 0. And let's say, I mean, of course, when I write on this, I mean, this is a flow, so it's depending on the initial condition. And then for each initial condition, you can sort of solve this differential equation, hopefully. But let's now know just, so let's now just fix the initial condition and define yt now just to be the flow started at this point, right? And so it means that we want to understand this type of equation. Okay? And we want to understand this now when Z is not differentiable. When is not C1, let's say. Okay. So how could we attack such a problem? Any ideas? Yeah, weak solution, yeah. Well, and then, yeah, okay, so potentially you could imagine that, fine, okay, Z is not C1, so, but okay, you can still make sense of this as a generalized function somehow. But the problem is that doing nonlinear operations on generalized functions doesn't really make sense. I mean, it's like having you want to square the Dirac delta. It doesn't make sense as a distribution anymore. So you cannot really do that. Yes, yeah.
There is one option. You're thinking here like
Yeah. We don't want to chase the E2. We want to do this for fixed realizations of the noise.
Then regularization,
Yeah, okay. So, okay, let me backtrack just a little bit. So, I mean, okay, we have a differential equation. Let's try to integrate it. I mean, usually integration is better. It's a nicer operation than differentiation. So let's try it. From S to T. And what do you obtain if you integrate both sides? Well, you should get the solution, yt minus ys, should be given by an integral on this form here. Okay? And so the increments of the solution should be given by an integral, and I'll just introduce some notation already here, because increments of paths will appear so many times. Whenever you see an increment like this, I will write delta y as t. So you take some path, delta y as t is simply the increment from s to t. Okay, and you can say, well, here we have the derivative of so dz dr, and I don't know, first year calculus course, what you would do is that you would just say, let's take away the dr like this. Okay? So perhaps this is better. Of course, the only thing I did was to postpone the problem, because, I mean, now the next question is, what's really meant by this integral here? What do we really mean by this? So now the question is this well defined? Okay, so of course, if Z was C1, we can really define this, but what if it's less regular? So let's try to push the regularity. And so the way we're going to measure regularity for these lectures is by something called p-variation. So, I mean, for all the other talks, they were using Hölder spaces quite a lot. Instead, we're going to use, and it's really more suitable for these type of equations, something called p-variation. P-variation.
Z is, for example, not C1.
Yeah.
Bigger than half.
Yeah.
Of course, I guess this makes sense as a young
integer. Yeah. We will get to this. Don't worry.
So I'm thinking like below half.
Sure. I mean, that's the ultimate goal. But I mean, and I will go through this. So let's go, first we will see exactly what you said, and we will see how it fails for this different type of regularity class, and yeah. So we say that a path, say a path h from 0 to t with values in, I don't know, Rd has finite p-variation, if so we look at, so we take some partition and we sum up the increments of the path, raise it to the power p, and we want this to be finite when we take the supremum over all partitions like this. Okay, and here the sup, where supremum is taken over all partitions. Over all partitions. Pi of 0 to t. Good. So we need another definition. which will sort of illuminate how p-variation paths are related to more typically like Hölder type paths. This would be the definition of what we would call a control. So a function or a continuous function I will write it like w, small w. It will be defined on, so okay, the simplex, which is simply s and t belonging to 0 to t squared, such that s is smaller than t. S smaller than t, taking values in R plus. We will call it a control. A continuous function is called a control. Control if it is subadditive. It is subadditive. Additive, which just means that if you look at w from s to u plus w from u to t, it is bounded by w from s to t. And this holds for all s less than u less than t. Okay, so why did I introduce controls? Controls gives us a very convenient way of measuring p-variation of some path. And so let's record this now as a little lemma. So the lemma tells us that H has finite p-variation if and only if there exists some control, W, such that the increments of the path is bounded by this control, in this sense, to the 1 over p. Okay. Let's even prove it. Or at least give a sketch. So let's assume now that we have, let's see how it's best to begin. I guess if we start now saying that we have finite p variation, then there exists some control. Yes. So let's assume that H has finite p variation. And now let's define WH as T to be the supremum over all partitions where we sum to the power p like this. So what we're doing is we're simply just intersecting the partitions here with the interval s to t. Okay? And now one can show, so I mean, we can show that this is a control. It's a bit technical, it's not so easy. I mean, what's a bit challenging is to show that this is a continuous function of s and t, but it's more or less a somewhat technical epsilon delta proof. So I won't go through that. So can show WH is a control. But now let's see that it dominates the increments of H. But if we now write delta of H as T, I mean, we can write this certainly as summing over this partition pi star like this, where pi star is just a trivial partition, right? It's just taking the endpoints S and T, right? So I'm kind of cheating a bit. Okay, let's write it down. Okay, but this is for a fixed partition pi, so of course it's bounded by where you take supremum over all partitions. All right, so this should be bounded now by WH as to T, and we need to raise it to the 1 over P power, right? Because this is defined to be the supremum over all partitions. Right, and here, where pi star is a very boring partition, it's just the endpoints S and T. Good, let's go the other way. Now let's assume that there exists such a control, such that increments are bounded in this sense here, and let's show that it has finite p variation. So take any pi, and let's sum it up to the power p. Well, now by assumption, this thing here is just bounded by W Ti plus 1. Good, but remember what we assumed for the controls is that they're sub-additive. Okay, so if we sum up all these points, we just get this. Or less, no, sorry, 0 to T. Right, and this is independent of the partition we chose. We're taking the supremum, we see that it necessarily has finite p variation. Okay. Okay. Okay, so we see that instead of, well, actually, I didn't give this a name now. I should have done this. Oh, sorry about this. I should have written, we want to define now semi-norms. So the p variation semi-norm of H should be given by this, and of course we need to now take the pth root here, like this. Oh, sorry. Good. So, but from this lemma, we see that we could have defined H in the p variation semi-norm as the infimum over all omega 0 to t, such that, sorry, not omega, but W is the control and increments of the past is bounded 1 over p. Okay, everybody on board? Any questions? Am I going too fast? Too slow? No? Okay. Oops. Let's see. Okay, so now we just need one technical lemma, and then we will return to trying to construct these integrals that I promised we would talk about. So the lemma tells us that if W1 and W2 controls, then so our, let's say W as T, let's say you take one control and you raise it to some zeta, where zeta is some number strictly larger than 1, then this is still a control. And yeah, let's call W tilde W1 s to t to the power alpha, W2 s to t to the power beta. And this holds only where the sum of the exponents needs to be something larger than or equal to 1. Then both of these are also controls. Okay? Yes. Okay, the proof is a nice exercise, I guess. Proof exercise. So for the first claim, okay, just to give you a hint. Hint is that if you take a to the zeta plus b to the zeta, this is bounded by a plus b to the zeta, when zeta is bigger than 1. So we should prove this. And the second one, to show that this one is a control, it follows by Hölder's inequality. And Hölder. Okay. So let's see. Okay, so now we will get to something interesting. Now we will sort of start to hint at something that has something to do with integration. And we will now look at it's an old result. It's a theorem by Young. From 1936, actually. And what it says is that if you take two paths, so you take H and G, with values in R, where G is, let's say, G is P variation. Let's say H is Q variation. And assume that 1 over P plus 1 over Q is strictly bigger than 1. Then this is enough to construct an integral. Then we can define, so let's see, how did I write it? GR, DHR. Where you construct this type of Riemann sum approximation. Then this is well defined. It's well defined. And we have a very nice description of this integral on small scales. What I mean is that integrating from s to t, gr, dhr, this is comparable to multiplying g by increments of h up to some constant c, and then let's say here we need to put g in the p variation and h in the q variation. So this is exactly what Ujjwal was talking about. Right? That sort of if the path is regular enough, there is a classical way of doing this, of constructing this integral. It was already known in 1936. Sorry? Yeah, and the Hölder version would be exactly the same. Yeah. Okay, so I will actually prove this. It's a beautiful proof. It's simple. I mean, you could teach it to, to somebody who's done a course in calculus. And I mean, it's also not as anachronistic as it might seem, because we will use these techniques quite a lot, and we will see how it pops up as a natural type of result that we will need later for rough paths. Okay. Good. Any questions, comments? No? Okay, let's prove this. First of all, let me define a new function. So now define psi st, which will not be the increment of some path, but it will be gs times the increment of h from s to t. This is a function of two variables, right? Okay, and now notice that if we compare psi from s to t and we remove how it behaves in some midpoint in between s and t, we subtract psi from s to u and from u to t. If you just do the computation, you will see that this is equal to minus g from s to u, then delta h from u to t, like this. Okay, and this is also a quantity that pops up quite a lot. So recall before I said that, okay, for parts, I will be interested in increments quite a lot. It was useful to have this type of notation. And now by slight abuse of notation, I'm going to call this quantity here delta psi as ut. Right? So here the delta was defined for parts. Here it's really defined for functions of two variables, s and t. Okay, so it all might seem a bit mysterious, but you should notice now that for the rest of the proof, I don't really care that psi is equal to exactly this thing here. The only thing I need is this psi should behave, oh, I should have said this, right? If I now multiply increments of g with increments of h, this is bounded by some control g from s to u to the power 1 over p, and then this from u to t to the 1 over q. Right? Because they're p and q variation. So there must exist these controls, which is bounded by some new control, w from s to t to the power, what will it be? Some theta, and let's see, how did I write it? Where theta is 1 over p plus 1 over q, which we know by assumption is strictly larger than 1. And let's see if I get it right. This is given by g s to t q over q plus p wh s to t, and then p over q plus p. Good. So, okay, so what I wanted to say before was that now for the rest of the proof, you will notice that's more or less the only thing that I'm going to use. I'm not going to use this specific form of psi. I'm just going to use that there exists some control that bounds it in this way here. And this will be incredibly useful for us later when we want to do rough path integration. Okay. Now, let's define some approximation of the integral. So let's say we have given some partition pi and define this I pi to be the sum over pi of this ti and then ti plus 1. Right, and you substitute for psi this expression here. This is exactly the Riemann type sum approximation that we want to have. okay, where pi is some partition. Okay, partition of S to t. And here comes a really beautiful trick, something really clever. Young must have thought a long time before he arrived at this. So let's now notice that there exists some index k such that this control that is bounding the delta of psi, so this control here, between tk minus 1 up to tk plus 1, it's not too big. We can bound this by 2 times the control over the full interval from S to T, divided by number of partition points minus 1. Okay, so this is the really clever trick. And why is this true? Well, if not, sorry? Yeah, you assume, exactly, you assume the opposite. Right, so you assume this is strictly larger than 2, right, and then you sum it up. You sum here over k. If you sum here over k, and now recall, okay, let's be specific here, so 0 to n minus 1, so there are, yes, so there should be n minus 1 points here. Right, sorry, of course. When I'm summing here, I cannot sum from 0 to n minus 1, right? Because this is starting one index before. So this has to be k going from 1 and n minus 1. So there are really n minus 1 terms here. Right, so this is equal to 2w of st. However, this is now we can use the subadditivity again. And one can show using the subadditivity that this is bounded by 2 to the w of st, like this. Okay, I'll leave this as an exercise, but it's not difficult to see. You need to split up this sum somehow, and then you use subadditivity sometimes, and what you will see is exactly this. So now we get something absurd, right? We get that 2 times w of st strictly larger than 2 times w of st. Right? This is absurd. So there must exist some index like this. Okay, so now let's compare a Riemann sum approximation to the one where we remove exactly tk. Now consider, let me see that I get the correct sign. Okay, so we take the partition and we just remove the time corresponding to this index here, to this k here. And we compare to the one where we're just summing over the full partition. And what we will see is that almost all terms cancel, except for what we will be left with is a plus 1, right? Because this term is certainly not here. Here we're all summing over consecutive points. But there will be 2 consecutive points here that we missed in this Riemann sum, which is tk minus 1 to tk, and then psi from tk to tk plus 1. Right? And okay. Right, this is exactly the quantity that I introduced here. This is this very useful quantity that pops up quite a lot. Right? And the notation I had for this was delta psi from tk minus 1, tk, and then tk plus 1. And now, notice that we only need to assume that this is bounded by tk minus 1 to tk plus 1. to the power zeta, where zeta is strictly larger than 1. And now let's plug in how tk was chosen, or this index k was chosen, right? We wanted this to be smaller. So that this is smaller than 2 to the zeta, w from st to the zeta, and then over n minus 1 to the zeta. Okay? Any questions? Okay. So we see that if we remove this particular point, we're not changing the value of this Riemann sum too much. And now we just keep iterating this. Now we have a new partition with one less points than from what we had before. So we can find a new such point that we can remove that doesn't increase the size too much. And then we can just keep on doing this. So we have some partition and we just keep removing and removing points. So we keep removing points until we get, I mean, we're basically left with nothing here, right? There will be nothing to sum over left. So we will get psi from st, and then this Riemann sum approximation, and then we keep adding and subtracting here. What we will get is, let's see that I get this correct now, just get the indices correct. So we get the sum of j going from 1 to n minus 2, 2 to the zeta over n minus j to the power zeta, and then w of st to the power zeta. Okay? We can factor both these, and so we get 2 to the zeta, or let's just write it like this. To the zeta, and then this will be bounded by some constant, right? This is summable as long as zeta is bigger than 1. We can send them to infinity. Times some constants, which depends only on zeta. Okay? This is what we would call the maximal inequality. And so we see that this is starting to look exactly like what we wanted here. Right? If you could somehow take the limit in this thing, we would be done for this inequality. Okay? But let's also show that it's Cauchy. Show that this I pi indexed over the partitions is Cauchy. Cauchy as the mesh of the partition is going to 0. Yeah, exactly. Yeah. Independent of the partition. Yeah, that's the beauty. That's the miracle. Well, miracle, I shouldn't say. That's why it's so nice. But I mean, it's just this quantity here, and then you change. Yeah. I mean, I guess it's the Riemann zeta function somehow. Sorry? That is Cauchy? This? What would follow from this, you mean? I mean, this is for a fixed partition, right? And I removed one point. But what I really want is that if you take any sequence of partitions, or any, let's say, net of partitions with mesh going to 0, you want that this one converges to something. Okay, so that's the next thing we want to do. So now let's take fix pi, and I don't know, let's call it pi prime, and define now pi star to be pi union with pi prime, meaning that you take the finest partition generated by these two partitions. And right, I mean, we want to show that this quantity goes to 0 as the mesh of the, as pi and pi prime are getting smaller, right? This is what we want to show. But now let's compare this to, so I pi and then I pi star. So we are just adding and subtracting I over pi star minus I prime, like this, okay? So label these 1 and 2. Okay, let's just keep this. Let's not remove this yet. Okay, but then we can see, it's not difficult to see. Let's now see that this term is going to 0 as the mesh of pi is going to 0. So the first term, let's see, how can we bound it? Yeah, we can write this as sum over j, let's say, and we will put side tj plus 1 minus and this, of course, has to be the finer partition like this. Okay? Right, we're just comparing these two Riemann sums, and this one is much finer than this. So, I mean, most of the terms will cancel, but we will be left with the sum over this. Okay? Now let's plug in the maximal inequality. So let's just plug in this maximal inequality. We see that this is bounded now by just summing w of tj plus 1 to the power zeta. Right? And the exponent here, zeta, is bigger than 1. So we can write this as zeta minus 1, and then w tj, and then tj plus 1. And we can extract this one. We can take this out of this sum. So supremum over all indices, ti, and then ti plus 1, zeta minus 1, and we'll be left with summing up over j, this w of tj, and then tj plus 1. And again, by subadditivity, this is bounded by w from 0 to t. Right? It's subadditive, so you can just place it like this. And this guy here certainly goes to 0, right? This exponent is bigger, strictly bigger than 0. And as the mesh of the partition goes to 0, we have something continuous. This must necessarily go to 0. Okay? So this was the first term, and the second term is exactly the same. Exactly the same argument. Exactly the same. Okay. Right? So, okay, we're done. It shows that this is converging, and of course, now if you take the limit, pi going to, mesh of pi going to 0 here, what you obtain is exactly what we call this integral here. Okay. Right? It's a beautiful proof. Right? It's really nice. It's really clever. Really, this choice of this index, it's done in a very clever way. Well, I think so, at least. Good. But what you should notice now is that I noted this in the beginning, that more or less the specific form of psi, that is g times the increments of h, is not really important. So in fact, we proved something which is much more general and abstract, and it will become very useful for us later. So in fact, we proved call this lemma. And this is something, you will hear it referred to as the sewing lemma, if you get into rough path theory. Sewing lemma. And what it tells us is that, suppose you take some function psi, defined on the simplex, is such that, right, so psi should now, oh wow. Psi is now a function of two variables. I'll finish really quickly. It's a function of two variables, but when you apply this delta operator, so that you get a function of three variables, if this is bounded by some control to some power zeta strictly larger than 1, then sort of this, I don't know, it's like an abstract integral operator. The integral, again, of psi ti plus 1 is well defined, and on small scales, this integral is well approximated just by psi. Okay, go through the proof, you see this is exactly what we proved. And then we somewhat just applied it to this particular choice of psi. Yes? Where did I write? Yeah? Oh, it's SUT. Yeah. Okay, yeah. Oh, I thought I wrote something wrong. Okay, yes, no, SUT. It's bounded by this, and then you can define this type of Riemann sum approximation of the integral. Good, okay. That's it. Questions or yes? Yeah. So if you put p equal to 1, this will be exactly the boundary variation. Except, no. I mean, I really required all my paths to be continuous. Or did I write that? Maybe I forgot to write it. But all these paths should be continuous. So, I mean, that's usually not required for the bound. Sorry? Sorry, I don't understand what you mean. Okay. Yeah? No. And that's, so I didn't have time to show this, but that's really the point. One would hope to sort of now apply this to some martingale, I mean, to a Brownian motion, let's say, but it falls just short of being possible. So this theory here is not sufficient to understand martingale integration. So that's kind of the point, and we will get to this next time. Yeah, so now we will see why this fails, but we will also see how to fix it. And how to fix it is really from this abstract type of result. Yeah. More questions? No? Okay.
So let's thank